This is lecture 22 of Physics 210A. Thermal physics. And today we are going to start discussing kinetic theory of gases. So we are now going into microscopic details, not in so much rigor, but look at properties of gases from molecular point of view. So in this case, what we'll do is see how molecules actually give rise to pressure, equation of state, and other properties. So today we are going to discuss only on the focus is going to be on equilibrium properties. Particularly, we are going to discuss about pressure and equation of state. So we are going to assume that gas is dilute, and that makes it close to an ideal gas, molecules move around with different speeds, and when hitting the wall of a container, apply a force on it. How do they apply a force on it? By momentum transfer, and that gives rise to pressure. So that's what we are going to focus on today. So for this, consider the wall of a container and a small area in it, A. And on this, molecules are coming from all around. They're hitting it. They may come from this side, they may come from this side, hit it, and get reflected. So in the process, they transfer momentum to the surface. And what we want to calculate is how much is the momentum transfer per unit area, per unit time. The momentum transfer per unit area, per unit time is equal to pressure. So we'll assume that molecules are moving around with different speeds, and Fu du gives the fraction of molecules that have speed between u and u plus du. So immediately you see that integral fu du is equal to 1. Now to calculate the pressure, again, let us consider this small area. And on this, molecules are falling from all around isotropically. So let's take an angle theta. Now, in per unit time, the molecules cover a distance v. So at this angle theta, in this area, the number of molecules hitting will be equal to the density n, number density n, times v times a cosine of theta, where a cosine of theta is this projection of the area perpendicular to the direction of motion. This is its speed v, and the fraction of these molecules is then obviously fv dv. What is the probability that the molecules are coming from this angle theta? I'm making this slightly big. So probability molecules coming at an angle theta is equal to d omega, where d omega is the solid angle at theta, divided by 2 pi, because 2 pi is the total solid angle, times the half. This half is because molecules can either come in or go away. Let me repeat this argument on the next slide. So what we are doing is we are considering molecules coming isotropically, and we are considering they coming at an angle theta. And from this angle theta, the probability is going to be at an angle theta. If I take a small d omega here, then d omega over 2 pi is the probability that these molecules are coming from angle theta, and 1/2 because from d omega molecules may come towards A or go away from it. So that gives you half the probability. And number of molecules coming with speed v is going to be fv dv, a cosine of theta times n. So if I integrate this, I get the number of particles. So number of particles coming to area A is equal to n by 2 d omega for times 1 over 2 pi. D omega is d phi, d cosine of theta, v a f v dv. And this is 0 to 2 pi. This is d cosine theta is 0 to 1, and this is going to be from 0 to infinity. So this is equal to n by 2, because this 2 pi cancels with this. Or there was a cosine theta here also. D cosine theta 0 to 1 gives you another half a integration v f v dv, 0 to infinity. So this is a, the area, times n by 4, times, by definition now, this is average speed. So this means number of particles coming out of this hole of small area A per unit area is going to be n by 4 v bar. Along the same lines, now I can calculate the pressure. Now for the pressure, again I write the number of particles coming in, and that is n 1 over 2 pi integration d phi integration d cosine theta times v fv dv. That's the number of particles coming in. dv will be integrated from 0 to infinity. And then I have each molecule transferring 2 mv cosine theta momentum. This is change in momentum of a particle striking that area A. So again, I can cancel this d phi and 2 pi. I get this to be equal to n, the mass, times 2 and there was a factor of 1/2 also. So there's a factor of 1/2 because the particles can go either way. And then I get times d cosine theta from 0 to 1. I have another factor of, which I am missing, was a cosine of theta. So there is an a. Cos square theta d cos theta gives you 1/3, and then I have integration v square f v dv, 0 to infinity. This 2 cancels again. So I get the force on this area A to be A times n m v square average divided by 3, because this term out here is v square average by definition. So pressure is force divided by the area. This comes out to be n m V square average divided by 3. This is P. And we have taken to be dilute gas, so this should be equal to N RT divided by, or this should be equal to nRT divided by n Avogadro number. That gives you the number of moles, V. This is gas is an ideal gas. So this immediately leads to n cancels, 1/3 m v square bar times n Avogadro equals, there's something wrong. There's there's a mistake, and we'll correct that now. So let's go to the next page, and we had written P equals N times 1/3 m v square average. N is the number density. I mistook it to be the number of particles. Since this is number density, I get P equals the total number divided by V, 1/3 m v square average, and this gives you PV equals N divided by 3 m v square bar. And this should equal the number of moles, so N divided by Na RT, because the gas is ideal. Now capital N cancels, and that gives you 1/3 n Avogadro m v square average is equal to RT. Now take R over Na to be K Boltzmann, and you get 1/3 m v square bar equals KBT, and therefore average molecular kinetic energy to be 1/2 m v square bar equals 3/2 KBT. That's the result of kinetic theory, and that immediately gives you that U, which is equal to the energy per mole, is going to be 1/2 Na m v square bar equals 3/2 RT. So kinetic theory plus ideal gas law gives you U per unit mole equals 3/2 RT, Cv equals 3/2 R, Cp equals 3/2 R plus R, which is 5/2 R. And this also gives you that the average speed square is equal to 3 kT by m. Now, we have assumed in this that there is a function f v dv that gives you the fraction of particles with speed between v and v plus dv. So now we will calculate this. And get Maxwell velocity distribution formula. So for this, these molecules are moving all around in x direction, y direction, z direction, and it's isotropic. So we assume that the distribution in all three directions is the same. Fvx dvx gives fraction of particles with velocity vx and in the range Vx plus dVx. Let me write it properly in the next slide. So I am assuming all these particles are moving isotropically in all three directions, and f Vx dVx is the fraction of particles that have velocity in Vx to Vx plus dVx range. By isotropy, f Vy dVy will give the same for Vy and f Vz dVz for Vz. So if a particle has velocity in the range Vx to Vx plus dVx, Vy to Vy plus dVy, and Vz to Vz plus dVz, then fraction of particles that have this is f Vx, f Vy, f Vz, dVx, dVy, dVz. Now, this is also asking, this is equivalent to a particle having velocity between v and v plus dv with v square equals vx square plus vy square plus vz square. Let's rewrite this. So I have f Vx, f Vy, f Vz, dVx, dVy, dVz is equivalent to fraction of particles with velocity v, velocity between v and v plus dv, where v square is vx square plus vy square plus vz square. All right, next argument. Is that this distribution cannot depend on the direction of v because of the isotropic nature. So let some function phi v square give the fraction of particles such that phi v square times 4 pi v square dv gives the fraction of particles with speed between v and v plus dv. So remember what we are doing. All we are doing is we are saying then that phi v square some d omega in v space times v square dv, that will be the volume in v space is equal to f vx f vy f vz dvx dvy dvz. So if you were to look in spherical polar coordinates, this is the volume we are talking about at distance v. This is dv, and there is some d omega v. And this is equal to fx and all that. So if this is the case, clearly fvx, fvy, and fvz, they also cannot depend on the direction. So because of the f vx cannot depend on the direction of vx, and therefore we assume that f vx is going to be of the form some constant c e raised to a vx square, and therefore f vy is going to be c e raised to a vy square, and f vz is going to be c e raised to a vz square. And now you can see what we did earlier. We had written that f v square d omega v v square dv is equal to, we multiply 3 f's, c cubed e raised to a v square times dvx dvy dvz. So this sits well. Phi depends on v square and the volume elements are the same. These are the volume elements, and then this is all consistent. So what we need to do now is calculate this A. This is again comes from kinetic theory relationships. Now, we know that integration fvx or fv dv minus infinity to infinity, which is equal to integration c e raised to a vx v square dv minus infinity to infinity is going to be equal to 1. And this gives you a relationship between C and A. But before that, we demand that Fv go to 0 as v goes to infinity, because there will be no particles with infinite speed. So let's put that minus sign in the exponential explicitly. Take b to be minus a, and therefore write fv dv equals c e raised to minus bv square dv. And now we want to calculate the c. So I'm going to have, through normalization, c integration minus infinity to infinity e raised to minus bv square dv equals 1. Now there's a trick to calculate this integral, which I'll put on the resources, and this integral comes out to be integration pi over b, and this is equal to 1. And this implies c equals square root of b over pi. So I get phi v square, which is product of these three, c cubed f vx f vy f vz, to be equal to b over pi cubed e raised to minus b v square. Next, we want to find b. For this, we use the result that v square bar is equal to 3 kt by m. And now calculate v square average through this. So v square average is going to be integral v square phi v square d omega v square dv, and v varies from 0 to infinity since we are using spherical coordinates. So this is equal to, I can do the d omega v integral directly, which gives me 4 pi integration b over pi raised to 3 by 2. This one is 3 by 2 here, e raised to minus bv square v raised to 4 dv 0 to infinity. So I get 4 pi b over pi raised to 3 by 2 integration 0 to infinity e raised to minus bv square v raised to 4 dv. This integral 0 to infinity e raised to minus b v square v raised to 4 dv can be written as d2 by dv square of integral 0 to infinity e raised to minus bv square dv. And this integral we have already calculated to be square root of b over pi. square root of pi over b. So this then comes out to be 3/8 square root of pi over b raised to 5 by 2. And this immediately gives you plug in all the things, and you get v square bar to be equal to 3 over 2b. So by constructing this distribution function demanding different physical properties, what we have obtained is that phi v square is equal to b over pi raised to 3 by 2 e raised to minus b v square, and we have found that v square bar is equal to 3 over 2 k 3 over 2 b. But from kinetic theory, we have v square bar equals 3 kt by m, and this should be equal to 3 by 2 b. And this gives you b equals m over 2 kt. And therefore, phi v square is equal to m over 2 pi kt raised to 3 by 2 e raised to minus mv square over 2 kb t. That's the Maxwell velocity distribution. So what I'd like you to do here is find f vx, f vy, and f vz individually. So Maxwell velocity distribution formula is that m over 2 pi kt raised to 3 by 2 e raised to minus mv square over 2 kbt times 4 pi v square dv. This fraction of molecules have speed between v and v plus dv in 3D. So let me conclude this lecture now. Concluding remarks, and these are pressure of an ideal gas has been obtained from kinetic theory, and 2, Maxwell velocity distribution formula has been obtained. Thank you.